We're going to look at two topics, the golden ratio and Fibonacci numbers. And I think you're going to see that these two topics are very closely related to each other. So to begin, we're going to look at about 10 minutes of a video called Donald in Mathmagic Land.
Hello, Donald.
That's me. Where am I?
Mathmagic Land.
Mathmagic Land? Never heard of it.
It's the land of great adventure.
Now, who are you?
I'm a spirit, the true spirit of adventure.
That's for me. What's next?
A journey through the wonderland of mathematics.
Mathematics? That's for eggheads.
Eggheads? Now hold on, Donald. You like music, don't you?
Yep.
Well, without eggheads, there would be no music. Come on. Let's go to ancient Greece, to the time of Pythagoras, the master egghead of them all.
Pythagoras?
The father of mathematics and music.
Mathematics and music?
Ah, you'll find mathematics in the darndest places. Watch. First, we'll need a string. Stretch it good and tight, plunk it. Now divide in half. Plunk again. You see? It's the same tone, one octave higher. Now divide the next section. And the next. Pythagoras discovered the octave had a ratio of 2 to 1. With simple fractions, he got this. And from this harmony in numbers developed the musical scale of today.
By golly, you do find mathematics in the darndest places.
You can imagine how excited Pythagoras was when he shared his findings with his pals, a fraternity of eggheads, known as the Pythagoreans. They used to meet in secret to discuss their mathematical discoveries. Only members were allowed to attend. They had a secret emblem, the pentagram. Let's see what the topic is for today.
What's going on?
It's a jam session.
Give me something with a beat.
Shh. So from these eggheads, the Pythagoreans, with their mathematical formula, came the basis of our music of today.
Pythagoras boy, put it out. Well, I'll be a frustrated kid.
It was our old friend Pythagoras who discovered that the pentagram was full of mathmagic. The two shorter lines combined exactly equal the third. And this line shows the magic proportions of the famous golden section. The second and third lines exactly equal the fourth. Once again, we have the golden section. But this is only the beginning. Hidden within the pentagram is a secret for creating a golden rectangle, which the Greeks admired for its beautiful proportions and magic qualities. The star contains the golden rectangle many times over. It's a most remarkable shape. It can mathematically reproduce itself indefinitely. All these rectangles have exactly the same proportions. This figure also contains a magic spiral that repeats the proportions of the golden section into infinity. To the Greeks, the golden rectangle represented a mathematical law of beauty. We find it in their classical architecture. The Parthenon, perhaps one of the most famous of early Greek buildings, contains many golden rectangles. These same golden proportions are also found in their sculpture. In the centuries that followed, the golden rectangle dominated the idea of beauty in architecture throughout the Western world. The Cathedral of Notre Dame is an outstanding example. The Renaissance painters knew this secret well. Today, the golden rectangle is very much a part of our modern world. Modern painters have rediscovered the magic of these proportions. Indeed, this ideal proportion is to be found in life itself.
Boy, oh boy, oh boy. This is mathematics. I got mathematical figures like that.
Donald.
Get me to it.
No.
Ideal proportion.
Not quite. No, I'm afraid not. Well, we can't all be mathematically perfect.
Oh, yeah? Yeah, I knew I could do it.
Now that you're all pent up in a pentagon, let's see how nature uses this same mathematical form, the petunia, the star jasmine, the starfish, wax flower. There are literally thousands of members in good standing in nature's Pythagorean Society of the Star. All nature's works have a mathematical logic, and her patterns are limitless. The magic proportions of the golden section are often found in the spirals of nature's designs. The profusion of mathematical forms brings to mind the words of Pythagoras. Everything is arranged according to number and mathematical shape. Yes, there is mathematics in music, in art, in just about everything. And as the Greeks had guessed, the rules are always the same. Well, Donald, did you enjoy your geometrical journey?
Gee, Mr. Spirit, there's a lot more to mathematics than 2 times 2.
There were lots of mathematical ideas talked about in that video. The one we're going to look at right now is the idea of the golden ratio, which sometimes goes by other names. Sometimes it's called the golden mean, or the golden number, or the divine proportion. So what is this golden ratio? Well, here's where it comes from. If we take a line segment and we divide it into 2 line segments and look at the lengths of those segments and create ratios from them, we're looking for something very specific to happen with the lengths in order to have what we call the golden ratio. So what has to be true is that the ratio of the entire length of the line segment to the longer of the 2 subsegments has to be equal to the ratio of the longer subsegment to the shorter subsegment. If we were to write that as a fraction, this is what it would look like. Now we're going to play with this idea a little bit so that you can get some idea of what would have to happen for this ratio to be true. So what I'd like you to look at is up at the top. You can see they actually are showing it as a line, but it's a line segment. There's a black one that has a 100 underneath it. So that 100 means that's 100% of the length of the whole segment that we're going to subdivide. And then up above that, you see something that's blue and something that's orange, and that's the divided line segment. So if we move this slider, we can change the lengths of these 2 line segments that the larger line segment's being divided into. So for example, if we divide them like that, we can see that the 2 shorter line segments represent 80 units and 20 units of our 100 units that the whole line segment has as a length. So if we look at those ratios, if we look at the ratio of the blue to the orange, the longer subsegment to the shorter subsegment, that ratio is 80 over 20, which is equal to 4. And then if we look at the ratio of the entire segment, the black, to the longer subsegment, which is the blue, that would be 100 to 80, and that ratio is 1.25. So 4 and 1.25 are not the same number. So what we're going to do is slide this slider to change these lengths of these line segments, these subsegments, and we're going to try to get the ratios to be equal to each other. So right now we've got 3.536 to 1.283. That's definitely not equal. We're going to keep moving this down. We're getting closer. 2.465 to 1.406. Getting closer. 1.914 to 1.522. Ah, right there. We've got it. So if we subdivide that black line segment into two pieces that are 61.8 approximately units and 38.2 units approximately, we get ratios that are equal to each other. So the ratio of the longer subsegment to the shorter subsegment is 1.618 approximately, and the ratio of the entire line segment, the black one, to the longer subsegment, the blue one, is also 1.618. So we found the place where we can divide this line segment up into two pieces so that we have these two ratios that are equal to each other. So let's go back to this proportion that we've written. If we think about this line segment that's being subdivided, and let's say we decide that the length of the shorter subsegment is 1 unit and the longer subsegment is A units, then together they would equal A plus 1 units. Now basically all we've done is we've taken the B that we started off with and replaced it with a 1. So now let's take a look at this proportion and see if we can use it to solve for A. So if we cross multiply, we've got a quadratic equation which we can put in standard form and then solve using the quadratic formula. And we end up with a value for A of 1 plus or minus the square root of 5 over 2. So we get two values for A. Now that value for A is what's called the golden ratio. And the letter, the Greek letter that's used to represent the golden ratio, is called phi. Sometimes it's called phi, and you'll hear me switch back and forth between the two sometimes. But that letter, that Greek letter phi, is either equal to approximately 1.618 or approximately negative 0.618. So it actually has two values. Now if we're thinking of a length of this segment, we'd probably say it's the positive value since we don't measure in negative values, although phi really does have two values. Now what does that really mean? Well, if we look at some things in the real world that seem to follow this golden ratio, then we can look at the relationship between the lengths of the parts of those things. So for example, if you look at the length of a human's arm, so from the tip of the finger to the wrist and from the wrist to the elbow, then we can see that golden ratio, which is approximately 1.618. Now how could we use that? Well, what if we knew that the distance from the tip of your finger to your wrist is about 7 inches? Then we could guess that the distance from your wrist to your elbow should be a little more than 11 inches. Now there are lots of examples of the golden ratio in the real world. As you saw in the video, architects have used the golden ratio. For example, on the Parthenon, the Greeks used the golden ratio when they constructed the Parthenon. Now, you might have a hard time seeing it in here because we don't see just a line segment. What you need to look at is those two segments that make up the lengths of the two sides of the rectangle. Those are the two segments which are in a ratio that's equal to phi. Now another thing you may notice is that those two segments are really making up this rectangle, which is called the golden rectangle. That golden rectangle is actually repeated within this larger golden rectangle. And in fact, what we're going to find out in our next lesson is how to use a compass and protractor to construct these golden rectangles. Now you'll also see the golden ratio and golden rectangles in art. You will see them in nature. This is Hurricane Sandy, or in a nautilus shell. And if you look at these three illustrations, you'll also notice these spirals that seem to be formed by the golden rectangle. That's called the golden spiral. Now the golden ratio is contained in these figures as well, and it may not be quite as obvious, although the pentagram is something that you saw in the video. So let's take a look at that pentagram and try to remember what was shown in the video about the parts of the pentagram. One thing that you saw was that we actually can form a golden rectangle out of parts of this pentagram. And another thing that you saw was that if we take some of the segments from this pentagram, that we can then see something interesting going on in the lengths of the segments. So for example, we've got these two orange segments that are the shortest and the second shortest segments. If we put those two together, the length of those together equals the length of the green segment. And if we take the second of the orange segments and put it together with the green segment, we get something that is the same length as the blue segment. The pattern that you're seeing here is something that was recognized by a mathematician named Fibonacci. Now Fibonacci noticed this pattern in nature, and there's a classic story about Fibonacci's rabbits, which goes something like this. Suppose we have two rabbits, they're babies, and those two rabbits make a pair of rabbits. In 2 months' time, those babies have grown to adults. We still only have one pair of rabbits. But now that they're adults, they can have babies of their own. So 2 months later, we not only have the two rabbits we started with, but we have two baby rabbits, and we have two pairs of rabbits in all. 2 months after that, the adult rabbits have more baby rabbits, another pair of rabbits, and the baby rabbits grow into adulthood. That gives us 3 pairs of rabbits. After that, the adult rabbits can have babies of their own, and the baby rabbits grow into adult rabbits. And that gives us 5 pairs of rabbits. And this obviously could continue for a very long time. Now if you look at the numbers we have for pairs of rabbits, 1, 1, 2, 3, 5, the pattern of those numbers is what's called a Fibonacci sequence. Now if you look at how that sequence is generated, if we take any two consecutive numbers in the sequence and add them together, we can get the next number in the sequence. So 1 plus 1 is 2, and 1 plus 2 is 3, and 2 plus 3 is 5. So 3 plus 5 would be 8, and 5 plus 8 would be 13, and we could continue this as long as we wanted to. So what on earth does that have to do with the golden ratio? Well, remember this. We had these line segments that came from this pentagram. And we said that if we took the two shortest segments and added them together, we would get something that's the same length as the next segment. So we've added two things together to get the next thing. And then if we take the length of that second segment and add it to the third segment, we get the length of the fourth segment. So you can see this follows that Fibonacci pattern. Now there's lots of things in nature that follow that Fibonacci pattern. We could look at the way that branches grow on a tree. We can look at the proportions in the human body. Or we can look at the proportions just in the foot. We can find that Fibonacci pattern, which means we can find the golden ratio in all of those things. Now the Fibonacci pattern is even contained within this flower and this pine cone, although it may not be quite as obvious. In the pine cone, what you need to do is count the spirals that either go clockwise, there's 8 of them, or counterclockwise, there's 13 of them. 8 and 13 are numbers in the Fibonacci sequence. In the flower, it's a little harder to count the spirals, but there's 34 spirals that are clockwise and 21 spirals that are counterclockwise. 34 and 21 are both numbers in the Fibonacci sequence. So if we look at that Fibonacci sequence and we want to try to find that connection between the Fibonacci sequence and the golden ratio, we can also look at pairs of numbers, and we can look for ratios between those pairs of numbers. So for example, the first pair of numbers is 1 and 1, so the ratio of 1 and 1 is 1. The next pair of numbers is 1 and 2, so the ratio of 2 to 1 is 2. The next ratio is, well, we have a 2 and a 3, so 3 to 2 is 1.5. And then if we make a ratio of 5 and 3, we get 1.66 repeating. Ratio of 8 to 5, we get 1.6. Ratio of 13 to 8, we get 1.625. And if you look at these numbers that we're getting for the ratios, they are getting closer and closer together. And in fact, if we continue this Fibonacci sequence on further and further and further, and we keep looking at these ratios, those ratios will get closer and closer and closer to phi. Now let's go back to this. We actually figured out this value for phi by solving a quadratic equation. What I'd like to do now is focus in on this. That is the exact value for phi, 1 plus or minus the square root of 5 over 2. And we're going to concentrate on just the positive part of that. There is a negative, there's a positive. We're going to pick one of those. So we'll pick the 1 plus the square root of 5 over 2. We'll also think about this line segment. And think about the fact that the shorter length has a length of 1. And then the longer length is a length of phi, which means together they're phi plus 1. Now what would happen if we would square phi? Well, that would mean squaring 1 plus the square root of 5 over 2. So if we would do that, we could multiply the two binomials together in the numerator and multiply the 2 and 2 in the denominator. We could combine the like terms in the numerator, so 1 plus 5 is 6. And now we're going to take that 6 and we're going to rewrite the 6 in the numerator as 4 plus 2. Now we've got one fraction. We're going to break this up into two fractions. So we'll write the 4 over 4 and the 2 plus 2 times the square root of 5 over 4. And now if we simplify both of the fractions, we get 1 plus the square root of 5 over 2. Now that fraction should look familiar because 1 plus the square root of 5 over 2, that's phi. So phi squared is equal to 1 plus phi. Now if you look at the picture, 1 plus phi is that length. So if we take those two shorter segments, the 1 and the phi, those two consecutive segments, and we add them together, we get another segment that we know has a length of 1 plus phi, which is equal to phi squared. And actually we could continue that. We could take these two segments, add them together, and we would have a segment that would have a length of phi to the third power. Now this sequence is called the golden sequence. So if we start with a sequence that, or a segment that measures 1 unit and a segment that measures phi units, we can simply add together consecutive segments to find segments that are powers of phi. So that's a lot of information about the golden ratio and the golden rectangle and the golden spiral and the Fibonacci sequence and how it all connects together. So as usual, read your book, do your homework, come to class prepared.